So we're going to continue with the Chapter 20 Vodcast notes by talking about what is the electromotive force that pushes electrons through an external circuit in a galvanic or voltaic cell. And secondly, how can we use a standardized table of something called reduction potentials to calculate the voltage of a cell? So as you see for the analogy here, water always flows from the top of the waterfall to the bottom spontaneously, because it's going from a region of high potential energy to a region of lower potential energy. Well, very similarly, that's what happens with electrons. When they flow spontaneously from the anode to the cathode, the reason why they're doing that is there's some energy position that's more favorable for them to move along. Now, this is shown on its side and it shows them moving down, but you could turn that battery or anything circuit-wise sideways and they're still going to flow spontaneously from the anode to the cathode as long as you have the proper conditions. So that's the electromotive force, the EMF, that pushes the electrons along their way. Now, we can calculate this difference in potential between the anode and the cathode, and we can call that the voltage. This electromotive force that pushes them along. And the higher that electromotive force, the greater the desire the electrons have to leave the anode and go to the cathode. We call this also the cell potential, and you'll hear me call it the voltage, as just sort of a shortcut. So this E of cell just means the voltage of a cell that's hooked up in a certain under certain specifications with certain chemical combinations. So we're going to measure that in volts. And the true definition of what a volt is it's 1 joule per coulomb. What's a joule? A unit of energy. What's a coulomb? It's a measure of the amount of charge. An easier way to think of this when I used to teach physical science was you can think of the electrons hauling through this external circuit carrying a little backpack of energy, and that backpack of energy would be the voltage. So what we're looking at here is a table that has been made by those proverbial people without the social lives. We call this a reduction potential chart. And even though you know that some things getting reduced have to have something that's being oxidized, to keep this table standardized and to be able to compare the potential to be reduced between two different substances, we've written them all as reduction reactions. So if you look on the left-hand side of every single arrow in this chart, you can see that they are gaining electrons. Now up near the top, where there's a really high potential voltage, positive 2.87, what that means is that fluorine, the element, really wants to gain 2 electrons to get reduced down to fluoride, the ion. Now that doesn't make much sense for me, so here's what my brain does. My brain knows that the reactive metals like lithium and sodium are very easily oxidized. So they're down at the bottom of the chart. They want to get oxidized more than anything. They don't want to be reduced. So the more positive that your reduction potential gets, the more likely you are to be undergoing a reduction reaction. And the more negative that it gets, the more likely you would be undergoing an oxidation. So you go, Misto, so how come if lithium likes being oxidized, why are we showing it as a reduction potential? Once again, to compare apples to apples, you got to flip the equation over, and by showing a large negative value for its potential, what you're saying in essence is that it has very low possibility of being reduced compared to everybody else and a high probability of being oxidized, but we still write it as a reduction half reaction. So this isn't a complete chart. You'll find a complete chart in the back of your book, and of course you would always be given this chart. And the way that they were able to, the anonymous they, measure these reduction potentials is by using something called the SHE, the Standard Hydrogen Electrode. And essentially, if you go back to that chart, see how the reduction of hydrogen is shown as 0? You need something to compare to. So they said, let's take a piece of platinum wire and let's have it operating under 1 atmosphere of pressure. So it's in a container that's got hydrogen gas over the top. Let's have it soaking in a bath of 1 molar hydrogen ions, so it's acidic. And we have a little platinum electrode here with a platinum wire that travels out to an external circuit. So within this, and we'll talk about it later, at both electrodes, you could be having a platinum atom donating electrons to turn hydrogen ions into hydronium. And you could also have, being reduced over at the cathode, hydrogen gas coming off. You don't need to worry about this right now. We'll come back to that. But the bottom line is you set up a standardized condition like you see here. Then they attach this circuit to other half cells that might have zinc ions with zinc electrodes, or it might be a copper ions that have a copper electrode. And they measure the potential between the two half cells compared to this puppy right here. Just let it go for now. It's not a big deal. But by definition, the reduction potential for hydrogen is going to be 0. And we're going to compare everything else to the ability of hydrogen ions to pick up electrons and become hydrogen gas. So let's let that one go for the moment. So keep this table here handy. We'll be using it quite a bit as we solve a couple of problems that are embedded into this PowerPoint as well as in the sample PowerPoint exercises. Okay. So let's take a look at the formula that's used to calculate the voltage of a cell. If someone gives you a table like that, it's pretty simple. You take the voltage, and so this is read as the cell potential. The little circly guy up there means under standard conditions. And if you take the cell potential, reduction potential of the cathodic reaction, the reaction that you figured out is happening at the cathode, and you subtract the cell potential, reduction cell potential, of the reaction that's happening at the anode, you got the voltage of the cell. It's really just that simple. In a way, in electrochemistry terms, it's kind of like our backwards way of thinking, how we always go products minus reactants. This is the Brown and LeMay textbook method of calculating the cell potential. Take the reduction potential of the cathode and subtract the reduction potential of the reaction happening at the anode. Even though we know that at the anode it's getting oxidized, just do it this way. There's another way, but I'll show you the Zumdahl method when I get back. Another interesting thing about cell potential or voltage is that it's an intensive property. So if you ever have to do something like use a multiplication to get coefficients or numbers of electrons to even up, you won't be multiplying the cell potential. And so that's an interesting property of voltage. It's based upon the energy per unit of charge. More on that later too. So remember this guy? One of the questions that you'd be given is, hey, look at a cell and tell me what's happening. Well, over here was oxidation because zinc atoms are losing electrons to become zinc ions. This has to be oxidation. Therefore, that must be the anode. And over here, we have reduction taking place because copper ions that are in the solution are picking up the electrons that flowed to them via the external circuit and turning into copper metal. Now, yes, I know this is an oxidation reaction, but we're going to flip it to find it on the chart, and we're going to go backwards. If I go and look at the chart, the reduction potential is going to be at the oxidation side, written backwards. From that chart, you would find a negative 0.76 volts. On the cathode side, it's already a reduction. You go and you find this guy in the chart. Let's go find it. I want to prove this to you guys. Here is copper right here, and it's showing that, oh, and you got to always be careful because there's different kinds of copper, as you guys know. So it's showing that we have a positive 0.34 is the reduction potential for what's happening over at the cathode. So we go backwards. It's going to be cathode minus anode. So if this is the reduction potential at the cathode, and this is the reduction potential for the reaction at the anode, written backwards, you simply go 0.34 minus a negative 0.76. and that's the same as adding a positive 0.76, the voltage that this cell would read once you close the switch and connect the external circuit is 1.10 volts. It's really just that simple. Now, in your sample exercises, and they're printed inside your PowerPoint notes, your lecture outline, there are two problems. I'm going to go backwards and do problem number 6 and then problem number 5. If you are given, and this looks scary at first, don't worry about it, it's just the dichromate in an acidic solution. And in a previous problem, in sample exercise 20.4, which you can go look at, some nice people have figured out the two half reactions. Now, once again, how can you figure out which one is happening at the cathode and which is happening at the anode? Let's do the easier looking one first. If we have iodide ions who have extra electrons turning into iodine, the element, the only way that could happen is if they're losing electrons. So this cell reaction here, this half cell equation, is showing something where we have the loss of electrons. So this is the one happening at the anode. Then by definition, the other half reaction that was pulled out of this main equation must be the reaction happening at the cathode. Dichromate ions, and specifically the chromium in them, are picking up electrons to turn into chromium ions with a 3+ charge. Remember, reduction is gain of electrons. So now that I know the two half reactions, I travel to that chart. And yes, this one is written as an oxidation, but in your mind's eye, just think of it as backwards. So we compare this to that. And when I go get the values, the cathode value for the reduction of dichromate to chromium is a positive 1.33. The standard reduction potential for this reaction written in reverse from the chart is a 0.54. So we always go cathode minus anode, boom, there is the voltage of the cell. Now, interestingly enough, up here in a step not really shown, to make the 6 electrons here in the dichromate half reaction equal the number of electrons in the anodic half reaction, somebody somewhere had to multiply one of these guys by 3. Well, remember, voltage is not extensive, it's intensive. It doesn't depend upon the amount. So you do not multiply by 3 if you have to do something, as I mentioned before, times equations by certain values to get the number of electrons lost and gained to equal each other. So that's the simplest kind of problem. Cathode minus anode. Get the reduction potentials off the chart, identify who is the anode and who is the cathode, and the reactions happening there, and the math is dead simple. In problem number 20.5, the only difference is that, again, looks like a familiar equation again. We saw in those previous graphics that the potential was reading 1.10 volts for that zinc and copper half cells. And so when you look at the picture, it tells us we have 1.10 volts total, and you can go look up on a chart that the reduction potential of zinc ions to zinc solid is a negative 0.76. So what we want to do is we want to calculate what's the reduction potential of the copper. So if I go back and remember this, if I remember correctly, if copper is being reduced, that means picking up electrons. So here was that blue copper ion picking up electrons, turning into copper metal. That's the one happening at the cathode. Therefore, if this is the one happening at the cathode, then that value will be punched in right here. But oops, we don't know what it is. That's what the question wants to know. Do you know the total voltage of the cell? Yes, it was given to you. Do you know the reduction potential at the cathode? No, pretend you don't have a chart. But you do know that the standard reduction potential of zinc is negative 0.76. So to solve using simple algebra, 1.10 volts, and this is subtracting a negative is adding a positive, but I have to subtract 0.76 from each side. The difference between the total voltage of the cell and the voltage that's happening, the standard reduction potential at the anode, is the standard reduction potential at the cathode. So it's just the same kind of problem, except this time the cell voltage was given and you had to find one of the missing reduction potentials. That's it. We will do lots of practice problems with these so that you get more comfortable recognizing who's being reduced, who's being oxidized, where is the cathode, where is the anode, what are the two half reactions, and how to use the chart to calculate voltage. Okay, I believe that we are at the end of this little mini lesson, and so I will say farewell until the next time. Take care.